Hello students, I welcome you all on this YouTube channel. Today we will discuss the load characteristics of DC shunt generator, right? So, this is the circuit diagram of DC shunt generator, right? This circle represents the armature, that is the rotating part, and EA represents the induced EMF across this armature. RA represents the armature resistance, right? So the word shunt means parallel. Shunt means parallel. So as you are watching here, this green one, this is a field winding. It is shunted across armature circuit. See here, it is shunted. It is connected in parallel with this armature circuit, right? Across this field winding is connected. So RSH is a field winding resistance, shunt field resistance, and ISH is a shunt field current, right? So this Vt is the voltage across this load terminals, right? Load on the generator is DC generator is electrical, right? So IL is the load current, RL is the load resistance, right? So now when you know that generator converts mechanical energy into electrical energy. So first of all, you need to give the rotation. You need to give mechanical energy to this rotor in form of rotation, right? So this omega represents the angular speed of this armature, that is basically a rotating part, basically rotor, right? So once rotor starts rotating in air gap, it will now cut the stationary magnetic field lines, right, produced by stator field poles, right, north and south field poles. These are the field poles, and these are the field lines. So these rotor conductors, they will cut the stationary magnetic field lines, right, and due to this there will be a change in flux with respect to time. So this change in flux with respect to time that will be achieved here, it is nothing but the induced EMF only, right? So this induced EMF will be developed in these rotor conductors, right? So now once induced EMF E is developed in the armature, that means voltage has been developed in the armature conductors. So now this voltage, it will produce a current in armature, that is armature current IA, right, in armature windings. So this is represented by this IA, right? Now, so the very first step is that you rotate this DC generator at a fixed speed, right? So now once it is rotated at a fixed speed, then the generated EMF, it will be fixed only, right? So have a look at it. What is the meaning of this load characteristic? Load means something external to the machine, right? Load means something external to the machine, right? So armature is internal, right, and load is external. So load means external parameters, that means load voltage, that is external voltage Vt, and load current, that is external load current, right, IL. So that means load characteristic means you have to plot a graph between terminal voltage, load terminal voltage Vt, and load current IL. That is the meaning, right? Between Vt and IL, you have to plot a characteristic which is known as load characteristics, right, of this DC shunt generator, right? So now see here, if the load resistance is RL, and if you are connecting the load in parallel, then load resistance will decrease, right? Because when you connect the resistances in parallel, the equivalent resistance will decrease. So once the load resistance will decrease, that means load current will increase, definitely, right? Because load is increasing, electrical load is increasing, so load current will also increase. So now that means once the load current will increase, that means from here you can write, see here, this is a load current IL, and this is armature current, and this is the shunt field current. So if you apply Kirchhoff's current law at this particular node, you can write IA is equal to IL plus ISH. Sum of incoming current is equal to sum of outgoing current. So this IA is equal to IL plus ISH. So here once the load is increased, load current is increased, then you can analyze that due to this increase in load current, you can say that armature current will also increase, right? So now if you are rotating this alternator, rotating this DC generator, if you are rotating this DC generator at a constant fixed speed, then the generated EMF will also be fixed. Now you can say that flux in the machine is fixed, right? You have not inserted any field rheostat to change the field current and field EMF and hence field flux. So this flux is having a fixed value. Ka is a constant for a particular machine, that means Ka is equal to Pz by 2 pi A. It's a constant for a particular machine. So E is only depending on the speed that you have kept a rated speed. That means once the speed is rated, it's a fixed, that means generated EMF will also be fixed. So now you can easily analyze that once the load current is increasing, armature current is also increasing, right? So that means if armature current is increasing from here, you can now conclude that if armature current IA is increasing, you can now say that for fixed armature resistance, which is winding parameter, is anyway it is fixed, and fixed armature induced EMF EA, the terminal voltage will reduce, right? Because armature current is increasing, right? So now you can sketch a characteristic, right? That is very easy. By increasing the load currents, your terminal voltage it is reducing. So suppose this is 50 volt, right? This is, let us say it is 100 volts, it is 150 volt, it is 200 volts, it is 250 volts suppose, right? So now if you note down these values of terminal voltage and the load current. So suppose you have connected a voltmeter here for measuring this VT, terminal voltage across load, and suppose you have connected a ammeter across an ammeter in series with this load, then it will measure this load current IL, right? So now you can measure this VT and IL both, alright, and once you take readings at 3-4 changing values of this load, you can easily sketch the graph between VT and IL, right? So here you will have, as you have understood, that once the load is increasing, load current is increasing, armature current is increasing, that's why terminal voltage is going down. That means you can readily draw a characteristic like this, right? It's a drooping characteristic, that means it is having negative slope. So this characteristic, that one, this is basically a DC shunt generator load characteristic, that means characteristic between terminal voltage and the load current, right? So thank you very much, thanks for watching.